Welcome to Spring LIB.
Hello everyone, today we're doing chapter 18, problem 64. In this problem, it asks us to synthesize each of these compounds from benzene and use any reagent that we need. So this is essentially retrosynthesis. So retrosynthesis asks us to start from benzene, working our way to get to this final product. So let's start with A. Well, in A, we see that we have chlorine and this R group, or this alkyl group, ortho to one another. So we need to add something that is ortho and para directing, specifically ortho directing. And we know that, for example, if I were to add the chlorine first, then yes, this would direct ortho and para. However, if I were to add this alkyl group through a Friedel-Crafts alkylation, then there would be a risk that this primary carbocation would be switched to a secondary carbocation, so I would get a mixture product. So therefore, I would need to add this as an acyl group. But acyl group would be actually electron withdrawing, so it would direct meta. So I would not get this product. So obviously, just by that sort of analysis, I know that I need to add the chlorine first. So I'm going to start off with my benzene ring, and I'm going to add chlorine and some sort of acid. And I will obtain my chlorinated benzene ring here, in which then I know this directs ortho and para, so then I can add my Friedel-Crafts acylation reagents, because I don't want to add the alkylating reagent, because there would be a 1,2 hydride shift to make a secondary carbocation, so I would not be able to get the straight chain carbon. I have 4 carbons, so I have 1, 2, 3, 4. I need my Lewis acid. And I'm going to get 2 products, one the ortho-derived, or ortho-substituted, and plus the para-substituted isomer. And I'm interested in this ortho. And what I need to do now is to reduce this carbonyl group so I can form the CH2 and straight chain alkane shown here. So I'll add zinc, mercury with acid. And remember, these reagents, it's good to just know what these reagents do. It's a little bit of memorization in organic chemistry that can help you a lot on your assessments. So we created product A. Well, what about in B? So B, we have a nitro and bromo group that are meta to each other. Well, we know that bromine is ortho and para-directing, but nitro is meta-directing. So obviously we would need to add the nitro first, so then we can have this meta substituted bromine group added thereafter. So this was A, so now we'll do B. So we need to first add the nitro, which is meta-directing, so then we can get that meta-substituted bromine. So I'll add the reagents needed to add the nitro. So HNO3 with sulfuric acid. That'll give me my nitro group here, and then I'll take that and add it with Br2 and FeBr3, just like in this step here, just different identities of your halide. I remember nitro was meta-directing, so we would only get one product in this example, and that one would be your product of interest. Very simple, 2 steps. So now what about C? Well, C, we have a carboxylic acid with a sulfonyl group ortho to it, but we don't know actually if I were to add the sulfonyl group first, then that would be meta-directing for here and here. So that wouldn't create the product of interest. So now if I were to add my carboxylic acid first, that would also be meta-directing here and here. So that wouldn't help me much either. But what about if I first added a carbon, which is ortho and para-directing, and then I oxidize that to a carbonyl at the very last step? Well, that would be doable, and then I would also get my substituted product as desired in this problem C. So first, let's add our methyl carbon. So I'm going to add my alkyl halide with AlCl3, and this is Friedel-Crafts alkylation, but the only option is to be a primary carbocation, so we're not concerned about any shifting because there's no carbons to shift with. And now we get our carbon substituted benzene, which is ortho and para-directing. So then I can add my SO3 H2SO4 to get both the para and the ortho substituted products. And after I get those, I could oxidize this methyl group to the carboxylic acid in the question stem. And I'm going to take my ortho substituted product of interest and fully oxidize that using KMnO4, potassium permanganate, to get my carboxylic acid. And ortho substituted product of interest. So now what about D? Well, D, similarly, we have carboxylic acid, but now a nitro group. And we see that these are meta substituted with one another. So what we can do is, well, we have two options. Both nitro and carboxylic acid are meta-directing. So we could add, just like in this step, add our carbon, our methyl group, then we could oxidize it to this carboxylic acid, and that would be meta-directing for here and here, and then add the nitro group then. Or alternatively, I can first add the nitro group, which is right away going to be meta-directing, then add the carbon group, and then oxidize that to my carboxylic acid. So those are two parallel steps, two parallel pathways, that produce the same results in the same number of steps. So it's really up to you which one you want to choose, but I'll just choose adding, for example, let's say we'll add the carbon first, just like in C. So I'm going to add my one carbon, just like in C. And I'm going to oxidize this now, so I get a meta-directing carboxylic acid first. KMnO4. And I'm going to oxidize this to the electron withdrawing carboxylic acid. So this is going to be meta-directing because it's electron withdrawing. And now I can add my HNO3 with H2SO4 to get my nitrated product, as in the question stem. So now let's do E, F, and G on the next page. So I'm just going to add in now we have E, F, and G on the next page. So now let's do E. So E, once again, we have a carboxylic acid, but now a bromine. Well, we know bromine are ortho and para-directing, and then we know the carboxylic acid is meta-directing, but if I first added this as a methyl group, then we know that would be ortho and para-directing as well. So once again, there's really no difference to which one I add, whether it be the bromine or the methyl group, but we know monobromination is quite difficult. It is doable, but it is more difficult than adding the methyl group, which is going to be para-directing, and then we can just quickly add the bromine group there. So, and then we can oxidize the methyl at the very end to get the carboxylic acid. So let's do that. So let's do E. So we'll start with benzene. Just like in C and D, we'll first add that one methyl, aluminum trichloride, Friedel-Crafts alkylation. And now we'll add our bromine. Remember, this is going to be both ortho and para substituted. So we'll have one isomer with the ortho and one with the para. And then I'll take my para and I'll oxidize the methyl group fully using KMnO4 to gain my carboxylic acid. Now what about F? So F is kind of more complicated. So we have carboxylic acid, chlorine, chlorine, and sulfonyl group here. So what we know is that if we add a methyl group first, so let's say instead of having its carboxylic acid, we added a methyl. Well, methyl is going to be ortho and para directing. So right away, we know that if we add the methyl first, then we can add these groups in thereafter. So that seems like the best choice right off the bat, because let's say if I was to add the sulfonyl group first, well, that's meta-directing only, so then we would only add the chlorines, but not the carboxylic acid, so we'd be missing out on this substituent. So right off the bat, we know that we should add in F the methyl group first. So we'll add our one carbon in Friedel-Crafts alkylation. Then we kind of have a choice. We can add the chlorines, or then we can add the SO3. But the issue is if we add chlorines, then we can get polyhalogenation, and we don't want that to happen. So let's add the SO3 first, just to occupy that para position, so then there'll only be the ortho available for attack. So we'll add the SO3 with H2SO4. Remember, this is going to attack both the ortho and para position, but we can isolate for the isomer of interest. So we'll have the ortho as well as the para. And I'll take the para and I'll add Cl2 a lot, so I'll say excess, and FeCl3. And then I will get attack on both ortho positions, just like I want in my final product. And now the very last step, just like in so many problems before, is that we need to oxidize the methyl group to a carboxylic acid. So I'll use KMnO4 to oxidize this methyl group. And now last but definitely not least, G. So let's see. We have some sort of R group or alkyl group here. And then ortho to that, we have a nitro. Then para to that, we have a chlorine. And we know that alkyl groups are directing ortho and para. So it seems like a good idea to add that alkyl group first. So then we can add our ortho and para substituents thereafter. And then we could simply oxidize the sp3 carbon, the sigma bond, into a pi bond using some sort of Markovnikov's elimination, or some sort of elimination reaction by the addition of a halide, and using that as a leaving group and adding a strong base to kick that off like we did in previous chapters. So let's start with, so this is G, so let's start with adding 1, 2, 3 carbons on that. 1, 2, 3, Cl, and I'll add AlCl3, and then we get a benzene ring, with the carbons that we want. And then we'll add one of these substituents at a time. We'll start with the nitro. Remember, you'll get two isomers, one ortho, one para substituted. So we want the ortho substituted, but we'll also get the para substituted, unfortunately, as well. But we can quickly just isolate that out. So we'll take the ortho substituted and move on, and we'll add chlorine to the para position in respect to the alkyl group. And we added one chlorine, but then we'll also get the isomer with the ortho isomer. Well, it's NO2, not NO3. NO2, and we'll also get the ortho isomer, but now we're only interested in this para isomer. So we'll take that, and now, if you guys remember, in order to oxidize these sp3 carbons to sp2 carbons to get an alkene bond, what we need to do is add some sort of leaving group, being one of the halides, and then we can use a strong base to have an E2 elimination mechanism. So let's add a leaving group on this benzylic carbon, and we'll do that by adding bromine and a radical initiator, being H nu. So this is through a radical mechanism. So we added bromine. And now if I add this up here, if I add a strong base, then I will deprotonate this alpha proton, and then this bond will go here, making a new pi bond, and then that will kick off your bromine group. So add a strong base, for example, potassium tert butoxide, and that will go through an E2 elimination reaction to form this product of interest.